Okay. So, sorry, there was a network issue. Fine. So, what we were talking here is with regard to the galvanic cell, and this is one of the important equation. So, cell potential is equal to cathode electrode potential and anode electrode potential minus anode electrode potential. Fine. So, this is one important equation. Another thing here is when I am talking about the galvanic cell, anode will be a negative electrode. So please remember, when I am talking about galvanic cell, anode will be considered as a negative electrode and cathode will be considered as a positive electrode. Anyway, last class we have discussed with picture. Now I am not going to draw the picture and all. That's where anode will be negatively charged electrode and cathode will be positively charged with respect to galvanic cell. Because when I am talking about electrolytic cells, so what do you mean by electrolytic cells? So electrolytic cells are those where there will be requirement of external voltage supply for the reactions to happen. That is called as electrolytic cells. So in these type of cells, anode will be positively charged. We will consider the anode will be positively charged and cathode will be negatively charged. So don't get confused. So anode will be positive, cathode will be negative. That is for electrolytic cells. But when it comes to galvanic cell, it is opposite, where anode will be negatively charged and cathode will be positively charged. Fine? So that's what you should remember when it comes to voltaic cell or galvanic cell, or which can also be called as a Daniell cell. A galvanic cell will be called as a Daniell cell when I am using at anode zinc plus 2 and zinc as a redox couple. A galvanic cell can be called as a Daniell cell when I am using at anode zinc ion and zinc as the redox couple, and at cathode it will be copper ion and copper as the redox couple. So under this condition, only under this condition I can tell it is called as Daniell cell. It can be called as Daniell cell. So what do you mean by Daniell cell? Daniell cell is nothing but a type of voltaic cell, or it's a type of galvanic cell where there will be generation of voltage due to the chemical reaction. There will be liberation of current due to the chemical reaction. However, why it is called as Daniell cell, or what is the speciality of the Daniell cell? So Daniell cell is a narrow term with respect to its person name. It's narrow term because it's applicable only for one condition, where anode will be having this redox couple and cathode will be having this particular redox couple. Fine. So that's what we have discussed in the last class. Fine. Then we were talking about redox potential. What is the indication if redox potential is having a positive value? What it indicates if the redox potential value is negative value? Right? So all these things it will help you for even in your competitive exams. Okay? So then we were discussing about redox potential, and I will continue with that now. Now when I am talking about redox potential value, that is if I consider standard redox potential value, then symbol will be E naught. This will be expressed in terms of voltage. Okay. So that's where we have the standard redox potential. So why it is called as standard redox potential? That is because during the measurement of, or during the finding of this value, they will make sure that the concentration will be either 1 molar if we are talking about a solution, or it can be 1 bar if you are dealing with the gaseous molecules. Got my point? So under this condition, if you are measuring the redox potential value, that will be considered as a standard redox potential value. Okay? So otherwise it can simply call it as a redox potential. So what do you mean by redox potential? Redox potential means it is the capacity of an element either to get oxidized or to get reduced. So in this case we can call it as reducing potential. In this case we can call it as reducing potential. That means how much it can reduce. That's why it is called as reducing potential. For example, we have zinc plus 2. It will accept the electron and it will become zinc. Okay, that's where reduction potential comes. Reduction potential of zinc ion, because how fast it's going to take up the electron. That's where the potential, reduction potential. Same way if I take the cupric ion, it will be accepting the 2 electron and it will become copper. So what I mean to tell here is, when zinc ion I am talking about, it will be aqueous, but when it will become zinc, it will become solid. That's what yesterday last class we have discussed. So what I mean to tell here is, I have 2 electrodes. So please remember, for 1 mark question, you can expect the definitions. So what do you mean by electrode potential? What do you mean by self potential or define self potential? So like that you can expect the question. So here what I mean to tell here is, reducing potential means in first case we have a zinc ion, it is accepting the 2 electron and it's becoming zinc. In the second case we have the cupric ion which is accepting the 2 electron and it is becoming copper. So what I mean to tell here is, I am dealing with the redox couple, that is zinc plus 2 zinc, and I am dealing with another redox couple, that is cupric and copper. Right? So always redox couple, when you are writing, oxidized part should be written first. Then comes the neutral part, okay, or reduced part. All of you have understood. That's where we have the representation of the redox couple. Now, when I am talking about zinc ion accepting the 2 electron, I will write approximate value. It will be somewhere around minus 0.76. Somewhere around minus 0.76, 0.76. When I am talking about the copper, once again approximate value, it will be somewhere around 0.34. I will express in terms of volt. So 0.34 volt. What I mean to tell you is, reducing potential or redox potential, when it comes to zinc ion or zinc plus 2 zinc redox couple, value is minus 0.76 volt. And when it comes to the cupric ion becoming copper, it will be 0.34 volt. So that means we have to focus on charges. So here it is positive, there it is negative. So what it indicates? So when I am talking about Gibbs free energy equation, delta G naught is equal to minus NF delta E naught. So that's where we have another important equation. Delta G naught is equal to minus NF delta E naught. Now if I substitute delta E naught value with the negative value, what will happen to the delta G naught value? It will become positive, because negative, negative, they will be positive. That means delta G naught value will become positive with respect to the first case. Right? So delta G naught value will become positive. Now if I put delta E naught value with a positive sum, with positive value, now what will happen to delta G naught value? It will remain negative, because already negative sign is there. So delta G naught value will become negative. Now, can any one of you tell me, in that case, which is the good acceptor of electron, whether cupric ion or zinc ion? Any one of you? Which should be the good acceptor of electron, whether it should be cupric ion or zinc ion? Based on this, even I have given the delta G naught value also. So which should be the good acceptor of electron, zinc ion or copper ion. That's why importance of the redox potential value or reducing potential value. Anyone? Delta G naught value is positive for zinc ion. Delta G naught value is negative for cupric ion or copper ion. So which should be the good acceptor of electron? Naturally both don't have the same value. That means there is a difference. One will be taking electron very easily, another one will be the poor acceptors of electron. So my question here is, which is the good acceptor of electron among these two, cupric and zinc ion? You can just mention ion name. Okay? It should be copper. Cupric ion should be the good. Okay. Fine? All of you are right? So that's where I can tell that cupric ion is the good acceptor of electron. That is because since it is having a positive reducing potential value, therefore delta G naught value is negative. That indicates that the process should be a spontaneous process. If you go back to the thermodynamics, delta G naught value if it is negative, gives free energy value if it is negative, that means that process is a spontaneous process. It will happen automatically. But when a delta G naught value, that is gives free energy value if it is positive, that process will not take place easily. Got my point? So therefore, you have to remember this equation. There might be some question based on this concept in your even in your competitive exams. Fine, all of you have understood. So that's where we have the zinc ion and copper ion. Zinc ion is the good acceptor of electron. Poor acceptor of electron, and copper ion is the good acceptor of electron when I am comparing zinc ion with copper ion. When I am comparing these two, that can be the statement where cupric ion will be the good acceptor of electrons. Okay, all of you have understood. So therefore, knowing the redox potential value or knowing the reducing potential value, then only we can design a particular electrochemical cell. Otherwise, we cannot design. We cannot decide which can be utilized as an anode and which can be utilized as a cathode. So to know that one, which particular redox couple should be done with respect to the anode and which should be utilized with respect to the cathode, to know that one we should know its reducing potential value. That's the advantage or that is the application of the reducing potential value. Okay, it's very important. This concept if you understand, it will be nice. Now when it comes to values, who told? It is minus 0.76 and it is 0.34. Who has told? Those chemicals cannot tell my value is this much. There should be something, right? So that's where we have the reference electrode. That's where we have the reference electrode. By referring to this electrode, we have taken those values. Always remember that reference electrodes, always it will be considered as a standard electrodes. Always it will be considered as a standard electrode. By referring to that electrode, we can tell that what is the reducing potential of another half cell potential. Got my point? In the last class we have discussed, when I am talking about galvanic cell, we will be having two half cells. Together they will make one particular cell. Anode half cell and cathode half cell. Right? That's what we have discussed. Now, with respect to the reference electrode, it will be occupying one particular half cell condition and another half cell will be to which we have to calculate the reducing potential. Very simple, I will explain it. So, before going for that, very important one is with respect to the reference electrode is standard hydrogen electrode. Standard hydrogen electrode. Okay, Earlier they used to ask with diagram and all. Now I think it's not there, but questions will be there. 1 or 2 marks question on this. It can be called as SHE, standard hydrogen electrode. Now when I am talking about standard hydrogen electrode, if I want to show it individually, that's where definitely there will be presence of the electrolyte. As any other electrochemical cells, there will be presence of electrolyte. Now what do you mean by electrolyte? If someone asks you 1 mark question, what do you mean by electrolytes? What do you mean by weak electrolyte? What do you mean by strong electrolyte? Then you should be in a position to give the answer. So these are the substance. Electrolytes are those substance which are in liquid or molten state, which has the capacity to conduct the electricity. That's why it is called as electrolytes. Why they have the capacity to conduct the electricity? Because they will give rise to ions, anions and the cations. So that's why we have the electrolyte. So when it comes to standard hydrogen electrode, since we are dealing with, in the name itself it is there, it is the hydrogen electrode. Naturally we are dealing with H plus and hydrogen. We are dealing with H plus and hydrogen as the redox couple. Right? Naturally, whatever ionic form is there, that should be present in the solution. That should be present in the solution. But very important point here is that will be of 1 molar concentration. That will be of 1 molar concentration, because we are talking about standard hydrogen electrode. Just like standard electrode potential, same as standard hydrogen electrode. So therefore, we have to maintain the concentration of 1 molar. We have to maintain the concentration of 1 molar. Okay, fine. So that's where we have the 1 molar H plus in the electrolytes. Fine. So naturally, as any other electrode, there will be presence of an electrode. There will be presence of a electrode. And that electrode, they will make sure that since we are dealing with the reference electrode, since we are dealing with standard hydrogen electrode, so we should make sure that those electrodes should not be involved in the reaction. Those electrodes should not be involved in the reaction. So that's where they will use a platinum electrode or a rod which is coated with platinum powder. That powder will be utilized to increase the surface area. If you recollect, in P block element, in Haber's process, they used to use heterogeneous catalyst. In what form they used to use? They used to use the powder. What is the intention? To increase the surface area. So why we have to increase the surface area? Because we are dealing with the gaseous molecules. Here also we are dealing with the gaseous molecule. This electrode, it will be coated with a glass which is enclosed. It will be coated with the glass. Okay. Now on the front side it will be coated with the platinum powder. Okay. It will be coated with the platinum powder. That is to increase the surface area, because we are going to fill this electrode with the hydrogen gas. We are going to fill the electrode with the hydrogen gas, because that is the one which will be another partner with respect to the redox couple. It is the hydrogen gas. So what should be the concentration of hydrogen gas? Since we are dealing with standard reference electrode, so therefore it should be 1 bar. It should be 1 bar. If you want to talk about Pascal, you can write, but you should give the value as 1 lakh Pascal. It will be given as 1 lakh Pascal. So I don't want in Pascal, I want it in ATM. So then it can be 0.987, I think. 0.98 I am sure. So 0.987 ATM. Otherwise very simple, 1 bar. But don't ever mention, some students they will mention 1 Pascal. It will be a wrong one. 1 bar is not equal to 1 Pascal. 1 bar is equal to 1 lakh Pascal. Okay, so they are not equal. So many students they will write, or they will write 1 atm. 1 atm, okay, fine. If I consider approximate value, fine. But otherwise it's not equal to 1 atm also. Atm is less than 1 bar. So that's where 1 bar hydrogen gas will be utilized. Pressure will be utilized since we are dealing with the standard electrode. Okay. So these are the conditions. Under this condition, this electrode will be considered as standard hydrogen electrode. Now, do you think this one has a galvanic cell? No. Because only one partner, only one electrode is there. What about another electrode? Right? So therefore, this is not a galvanic cell. This is a representation of one electrode, that is standard hydrogen electrode. Now, if I want to represent, one mark question you can expect. If I want to represent this hydrogen electrode, how to represent? Anyone with respect to galvanic cell? Already we have discussed. So in that case, how to represent the standard hydrogen electrode? So we have to start from the electrode. We have to start from the electrode. Then we have to come to the gas. Because electrode is in contact with the gas, then it is in contact with the liquid. So that's how it has to be mentioned. So we can mention that first one as platinum, because it is a electrode. So platinum, which is in contact with what? It is in contact with the hydrogen gas. It is in contact with the hydrogen gas. What is the concentration? Concentration is 1 bar. Concentration is 1 bar. Now, this is in contact with H plus. What is the concentration? 1 molar. Oh, sorry. Another line should not be there because we don't have another half cell. So therefore, this should be the representation of the standard hydrogen electrode. So platinum is in contact with hydrogen gas. Concentration we have to mention. Then it is in contact with the H plus, that is electrolyte. We have to mention the concentration. But please make sure that we have to mention the concentration. That will be appropriate one. And if you want to talk about physical form, then you can mention this one as aqueous. You can mention this one as aqueous. H plus is in solution. All of you have understood? So this is where we have the standard hydrogen electrode. Fine? What they will do is, they will connect this half cell. Now we have got one half cell. Now it will be connected to another half cell. It will be connected to another half cell. Where, for example, if I take copper. If I take the copper, that means copper plus 2 and copper as the redox couple. This will become treated. This will be treated as an anode. And this will be treated as a cathode. Okay? Another one will be treated as a cathode. Naturally, they will be connected. They will be connected with each other. Fine? So that's how I have got the electrochemical cell now. The whole cell is ready. One half cell with another half cell. Now it is complete. Okay? Now, whenever they are connected with each other, they will find out the value in voltmeter. They will find out the value in voltmeter. That means they got the value of somewhere around 0.34 volt. That's where they came to the conclusion for this particular value. Because when she, that is standard hydrogen electrode, was considered as the anode, and when it was connected to cathode as another half cell, now the value on the voltmeter, it was somewhere around 0.34 volt, which is going to measure the voltage, potential difference. Which is going to measure the potential difference. That's where the value was somewhere around 0.34 volt. That's how we have got the value. That's how we got the value for copper plus 2 accepting the 2 electron and becoming copper. That's where we have got the value as 0.34 volt. Because for standard hydrogen electrode, that is H plus, accepting the electron and becoming hydrogen gas. Please observe the equation. Since I have mentioned one electron, I have written as H plus. Since here 2 electron, I can take it as 2, then I can make it as 2H plus, then I can remove the half. Then I can remove the half. So that's where we have the reaction. So this is a reaction at anode. This is reaction at cathode. So what it tells? This value tells that cupric ion can take up the electron from the hydrogen. Cupric ion can take up the electron from the hydrogen because we have assumed this value as 0 volt. We have assumed this redox couple value will be as 0 volt. That's why it is called as standard. We have assumed the value of 0 volt for the standard hydrogen electrode. Reducing potential or reduction potential for she is 0 volt. One more question was there. What is the reduction potential value for standard hydrogen electrode? Then the answer is 0 volt. That's all. You will get 1 marks. So that's why it will be taken as 0 volt. And the value was 0.34 volt. That indicates that hydrogen will give the electron to copper, or in short I can tell that copper plus 2 plus hydrogen getting converted into copper and 2H plus. This will be the reaction. This will be the net reaction. Okay? So where hydrogen is going to donate its 2 electrons to cupric ion, so therefore copper will be formed and therefore H plus will be released. What my point, all of you? So this is the net reaction. If I take zinc, so we will remove this particular half cell and we will replace this half cell with the another half cell which is having redox couple of zinc plus 2 and zinc. It will have a redox couple of zinc plus 2 and zinc. Now the situation will be different. If we imagine this one as a cathode, okay? So where zinc plus 2 accepting the electron and becoming zinc, we have got the value as minus 0.76 volt. Okay, minus 0.76 volt. This part is safe. So that negative value indicates that electron is reversed. Electron is in reverse direction. It is flowing towards the hydrogen electrode. So what I mean to tell you is, I have to change this equation. It's not cupric ion, it will be zinc. And it's not hydrogen gas, it will become H plus. And in the product side, it will be exactly changed. Here it will be hydrogen and here it will be zinc plus 2. Whether I am clear? So that's what this negative value indicates. Negative value indicates that electron has started flowing in the reverse direction. Electron is started flowing in the reverse direction. That means zinc can donate the electron to H plus, but copper will not donate the electrons to H plus. Whether I am clear? All of you have understood? Any doubts? If you have any doubts, you can ask. These are all some of the important concepts. One mark question you can expect, but based on this, you can understand further this particular topic easily. Fine? So that's where zinc is the good donor of electron compared to copper. That's what redox potential value we have got by considering the standard hydrogen electrode. Okay? Therefore, there can be a question. I think it's there in your textbook also. There can be a question. For example, I have a copper. If I put it in HCl, what will happen? Whether copper will be denatured or copper will be vanished or the copper rod will remain as it is. For example, I have a copper rod. This is a container. In that container, I have kept the copper rod. Okay? And this solution is having HCl. Maybe 1 molar or whatever it is. We have the HCl. So what will happen to the copper rod? So whether copper rod slowly it will get melted, slowly it will be dissolved into the HCl, what will happen? No need to worry, nothing will happen. Because just now we have discussed that copper can become or converted into solution when it will become iron. Then only it will go into the solution. As a copper, it is solid, so it should be written that side. Copper as it is a solid. We have taken the copper rod. But that solid can be dissolved only when it will become iron, cupric iron. Then only it will be dissolved into the solution. That is possible when copper will donate its 2 electrons to H plus. Its 2 electrons to H plus. So therefore hydrogen gas will be formed. That H plus will be present in HCl solution because HCl is a strong acid. So that will be present in the HCl solution. So a copper is going to get dissolved in HCl when copper can donate its 2 electron to H plus, where H plus will become hydrogen gas and copper will become cupric. Then only it is possible. Okay? So then only it is possible. But in reality, this is impossible. This is impossible. That's what just now we have seen. Copper is not going to donate the electron to the H plus, but H2 can donate the electron to the cupric ion. Okay? But here we don't have cupric ion, we have the copper. So no reaction will happen between the copper rod and the HCl. The reason is due to the difference in the redox potential, or copper is the poor donor. Copper will not donate the electrons to H plus. So therefore reaction cannot happen. But at the same time, if I take zinc rod, at the same time we will assume we have HCl and we have taken a zinc rod. We have kept it into this solution. Okay? So where HCl is there. Now what will happen? Slowly zinc rod is going to decrease in its size. Why? Because zinc will donate its electron. Zinc is going to donate its electron and it will become zinc plus 2, which will be dissolvable in the solution. It will get dissolved in the liquid, in the electrolyte. So this H plus will be taken by H plus. This 2 electron will be taken by the H plus, which will become hydrogen gas. So what is the net result? Net result will be decrease in the concentration of HCl, or acidity is going to get decreased. There will be liberation of bubbles due to the liberation of hydrogen gas. That is one thing. And there will be decrease in the size of the zinc rod. That's what we can assume. Fine? So therefore, whenever copper rod is kept in HCl, it's not going to dissolve. But it's not applicable for all the acid. Same copper rod, if I keep it in nitric acid, it will be having reaction, because in the nitric acid we have another partner which is called as nitrate ion. That's going to react with the copper. That's going to oxidize the copper. Okay? All of you have understood? So copper cannot be stored in HNO3, but copper can be stored in HCl. No problem. Fine? Hagadre. If you see the electrochemical series, on the top, we have a reaction which tells that fluorine, which is a gas, which is becoming fluoride. Okay? Same way, on the bottom of the electrochemical series, we have lithium plus 1, which is going to accept the fuel. Naturally we require 2 lithium, and it will become 2 lithium plus, plus is not there, 2 lithium. Okay? So now these are the 2 extreme reactions in your electrochemical series. Lithium belongs to alkali metal, fluorine belongs to halogens, right? So that's why, but here we are not talking about fluorine atom, here we are talking about fluorine molecule. So here we have the lithium ion. Now this particular reaction is having negative value, and this particular reaction will be having highest positive value. It will be having highest positive value, and this will be having highest negative value among all the elements. You can observe this one in your textbook also. They have given one particular table. So there you can observe even these reactions, where lithium plus with accepting the 2 electron is having highest negative value, and fluorine gas which is accepting the 2 electron and becoming fluoride, they are having highest positive value. Now by utilizing these two, by knowing their values, highest positive and highest negative value, now I can give a statement. Now I can give a statement that fluorine, that means fluorine molecule. So fluorine molecule is a very poor, listen to me carefully, fluorine molecule is a very poor reducing agent. All of you will understand, is a very poor reducing agent. Reducing agent. And I can tell that fluoride is a very poor, fluoride is a very poor, sorry, actually it should be reverse. Fluorine is a very poor, fluorine is a very strong, fluorine is a very strong oxidizing agent. Sorry, I was writing reverse. Oxidizing agent, and fluoride is a very poor reducing agent. I was writing reverse. Reducing agent. All of you got the point here? Fluorine gas is a very strong oxidizing agent because they will take the electron from other elements easily. So they are oxidizing the other elements, right? So they are very good oxidizing agent. But reverse, on the other side, fluoride is a very poor reducing agent because they are not going to donate the electron easily. So they are very poor reducing agent. Now what about lithium? Lithium plus, anyone? Based on this statement, can you give the statement for lithium plus? So lithium ion is a very poor oxidizing agent. Exactly reverse, oxidizing agent, because they are not going to take up the electron easily. So they are very poor oxidizing agent. If I take lithium, lithium is a very, can anyone? Lithium is a very lithium is a very strong oxidizing agent. It's a very strong oxidizing agent. Because they can donate the electron very easily. They can donate the electron very easily. So lithium ion, it will not take the electron very easily. So therefore lithium is a, okay, here also once again, oxidizing ion. Lithium is a very strong reducing agent. Okay, got my point? So lithium can donate the electron easily, but lithium plus will not take the electron easily. Therefore lithium can donate the electron easily. Therefore they have the highest negative value. So therefore lithium, since it is a very, very strong donor of electron, they will be having strong reducing action. So that's what these statements talks about. That's what these statements talks about, where fluorine molecule is a very strong oxidizing agent. Why fluorine molecule is a very strong oxidizing agent? Because it's a good acceptor of electron. Okay. Now, fluoride is a very poor reducing agent. Why? Because fluoride is not going to donate the electron easily. So therefore, they are very poor reducing agent. Lithium plus is a very poor oxidizing agent, because lithium plus is a very poor acceptor of electron. And lithium is a very strong reducing agent, because lithium can donate the electron easily. All of you got my point? So this is what we have the conclusion from your electrochemical series. This is what we can conclude from the electrochemical series. Fine? Okay. So in that case, I have got some questions. Okay, may not be directly from your board exams, but related question you can expect. Okay, so how much you have understood will come to know. Now, first one, two half cell reactions, two half cell reactions, two half cell reactions of an electrochemical cell, of an electrochemical cell. Two half cell reaction of an electrochemical cell are given below. So first one, this one you have discussed in your redox reaction, aqueous plus 8H plus aqueous plus 5 electrons and becoming Mn plus 2 aqueous and 4 H2O liquid. So here E naught value is 1.51 volt. 1.51 volt. Next one, stainless, that is aqueous, getting converted into stannic, 4 plus aqueous by giving the electron, and the E naught value for this one is 0.15 volt. Okay, all of you can see the equation. It is, first one is permanganate, MnO4 minus. In the acidic condition it will take up the electron and it's becoming manganese ion. And in case of the second one, it's a tin related ion, that is stainless, is becoming stannic by donating the 2 electron. And that's where we have the standard redox potential value. Now the question here is construct the redox equation. Construct the redox equation. Construct the redox equation from the two half cell reactions. From the two half cell reactions. Construct the redox equation from the two half cell reactions and predict the if this reaction favors the formation of reactants or product in the equation, and predict the, that means whether it will go for forward or backward reaction. So predict the reaction favors formation of product or reactants, formation of product and reactants. Got my point? So what you have to do here is, first you have to write the equation, redox equation. Then you should predict, based on that redox equation, you should predict that whether a reaction will be favorable towards the product formation or it is favorable towards the reverse direction. Can you solve it? It's very easy. So I will remove this lower one so that I can use the equations. First you should write the Redox equation. This type of question was not asked in board exam and all. Okay? It was from some other exams. I think from CBSE. Okay? All of you can see the board, right? I think we have low attendance. What is the reason? Fine. If I want, first I will write the equation, Redox equation. Redox equation is nothing but we have to talk about anode half cell reaction and we have to consider the cathode half cell reaction. Yesterday whatever I have told, and total cell reaction is nothing but Redox equation. Okay? So if you observe here, permanganate, what is the oxidation state of manganese? It is +7. So from +7 it is becoming +2. That is the charge on the iron. Here it is +2, which is the charge, that is the oxidation state. Now it is becoming +4. Now it is becoming +4. Right? All of you will agree with that. Now it is becoming +4. Hagadre, my question here is how to write the equation. How to go about the equation. That is the hint I have given. Anyone? It's very simple. We have to multiply this equation by 5. We have to multiply this equation by 2 to make the number of electron constant. So therefore, this equation I will multiply it by 2 and this equation I will multiply it by 5. Right? So that means I am going to get 2 MnO4 minus plus 16H plus 10 electron, which is becoming 2 Mn plus 2 plus 8 water. This equation I am multiplying it by 5. So therefore it will become 5 stannous iron, which will get converted into 5 stannic iron. Then it will be 10 electron. So I have to add it up. Okay. So 10 electron will get cancelled. So whatever I have left over is MnO4 minus 16H plus 5 stannous iron, which will get converted into 2 Mn plus 2 plus 8 water and 5 staining iron. All of you have understood? So this is the equation. Redox equation, which you have studied in your first PU. Okay? So this is the net equation by these conditions. Okay? Now, we have to find out, next point is that whether it will favor the forward direction or backward reaction. So what I mean to tell here is whether according to this equation they have given the standard redox potential value also. So whether manganese Mn plus 2 is going to donate the electron to staining, that is staining ion, or stannous ion is going to donate the electron to manganese, permanganate. That is the question. Whether this equation will go this direction or this equation will go in forward direction. That is the question. How to find out? How to tell that one? How to tell that one? We have to go with the values. Say for example, I want to see the cell potential. I want to have the cell potential. So cell potential is equal to cathode, cell potential with half cathode, half potential of cathode, and another one is related to anode. Another one is related to anode. Now I will consider permanganate. Whatever first equation is that is related to anode. I will substitute the value. So what is that value they have given for anode? Okay, 1.51, right? So 1.51. So what about cathode? It is 0.15. So what is the cell potential value? Whether it will be positive or negative? It will be negative value. So therefore, this cannot be done. This is not acceptable. Cell potential cannot be negative. If it is becoming negative, that means that particular anode, cathode, whatever we have taken, it is wrong. So in that case, I will reverse it. E cell is equal to E cathode minus E anode. Okay. Now, in this case, I will take cathode with 1.51 volt. That is related to permanganate. And then I will take the anode as 0.15 volt. That is related to stannous ion. Now what will happen to the final value? That will be positive. That will be positive. It will have the positive value. That means this one is acceptable. That one is acceptable. Or if you got my point, any doubts related to this? Where I am having a cell, E cell is equal to E cathode minus E anode. This equation already we have discussed. Now first I will substitute cathode value, anode value. If I am getting negative, then I have to reverse the condition. I have to reverse the condition. So that's where I have reversed the condition. Where cathode will be 1.51 volt, that is related to permanganate. That means this equation should be in the reverse direction, where this is going to be manganese ion is going to accept the electron. That means whatever stannous is there, it should come on in that direction. This reaction is not possible according to those values. According to those values. All of you have understood? So that is based on the cell potential, and that is based on the electrode potential. We can calculate the values. All of you have understood? Fine. Any doubts in this? So anyway, this type of questions was not there for your board exams and all, don't worry. But if you have understood the concept, whatever we have discussed, if you have understood the concept, whatever we have discussed, then you can apply your knowledge here and you can solve it off. Okay? So redox equation, first we have written the balanced redox equation. Then we have found we have calculated what will be the cell potential, where one redox couple will be permanganate and Mn plus 2, and another redox couple will be stannic and stannous. Okay, so that's where we have the conditions in this case. Any doubts? Any doubts? Okay, anyway, I will stop here. If you have any doubts, you can ask. Tomorrow, once again, we will have some questions that might be related to your board exams only, and we will solve those questions. Fine? But please remember, related to this, they will give redox potential value and you should predict which will be the cathode and which will be the anode. That question you can expect. Okay, na? Okay. Tomorrow we will continue. Thank you and take care.